feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson. We're starting a new unit, and in this new unit we are starting to look at function operations. So today we're going to begin the section of arithmetic and compositions of functions, focusing primarily on arithmetic in the domain of a function. So we're going to jump right into some example problems, and you can follow along with your notes PDF that it was posted on Google Classroom. The first thing that we're going to look at are the sums and differences of functions. So we know what sums and differences are. It's the addition and subtraction. Here in this case we're going to look at what happens when we add and subtract functions and how does that affect their domain. So we have kind of a generic rule. And this generic rule says that if we have functions f and g and they have corresponding domains p and q, then if we take f and g and add them together, that would be the same result, or add or subtract them together, that would be the same result as evaluating for f and g and then adding or subtracting together. And we're going to see that example in some example problems here when we start working with some real numbers. The big thing to notice here is that the domain is going to be the intersection of p and q, or the domain of f is going to be, the domain of f plus or minus g is going to be the intersection of the domain of f and g. So we know that notation here. And so if we take a look at problem number 1, before evaluating or before adding or subtracting these functions, the first thing that we want to do is determine the domain of h of x if h of x is the result of f and g subtracted and then evaluated by x. In order to do that, we basically want to take a look at the domain of the individual pieces. So the domain of f in this case, f is x squared. So the domain we know of f is going to be all real numbers. It is a polynomial without restrictions on the domain, and so it's going to have a domain of all real numbers. G of x is a line. So the domain of g is also going to be all real numbers. So then now our domain of h of x, which is the goal of what this problem is asking for, has to be the intersection of the domains of f and g, essentially where their domains overlap. And the overlapping of those domains would be all real numbers. So if we were to take h of x is the subtraction of these two functions, and we could do that in our calculator, we would see that the domain would go from negative infinity to positive infinity. So without doing any arithmetic or computations with the functions, we can look at the domain of the individual pieces and determine what the domain would be if that function was added or subtracted to one another. Now, if we take a look at problem B starts to get into the different ways that we can evaluate the function. So part B says to evaluate h of 3 using the definition. Well, if we take a look at what we wrote up here, this definition, this property, h of 3 can be written as, in this case, f minus g of 3. Because we know h of x is f minus g of x. Well, f minus g of 3 is the same as f of 3 minus g of 3. So we can do some quick substitution into the individual functions to evaluate what 3 would be in those individual functions. So 3 squared, which is f of 3, would be 9. 2 times 3 minus 9, which is what g of 3 would be, substituting 3 into g, is a negative 3. So h of 3 can be evaluated by first substituting into f and g separately, then subtracting those values. So 9 minus a negative 3 would be 12. So h of 3 in this instance is 12. Now in part C, what we're actually going to do is find a different way to evaluate h of 3. So C says write the new function rule for h. Again, h of x is the subtraction of these two. So essentially, h of x is written, again, we said, as f minus g of x, which can be substituted as f of x minus g of x. Well, we know what f of x is. It's x squared. And we know what g of x is. It's 2x minus 9. So if I substitute into this, and this is taking kind of many steps to get to the general subtraction of the two functions, what we get is x squared minus 2x plus 9. So this is another way to express h of x. H of x was given to us as a subtraction of two functions, and we can then create its own function by following through that subtraction. Now in D it says use the result in part C to evaluate h of 3. So if I use h of 3 in this case, I would be substituting 3 into h of x. So this would be 3 squared minus 2 times 3 plus 9, which is 12. So what we may notice here is that the answer in part B is the same as the answer in part D. We went about it differently. In part B, we substituted in the values for 3 into f and g separately, and then combined through subtraction. In part C, we combined the equations through subtraction and then substituted. In either case, we get the same answer. This is essentially what the definition is referring to. That substitution can be done before or after the combination of the functions through addition and subtraction. And regardless, either way, you're going to get the same evaluation. So if you can kind of follow that process, go ahead and pause the video at this moment and see if you can do problem number 2. Hopefully you got a chance to take a look at problem number 2. Problem number 2 takes us up just about a little bit here. The first thing that we're asked to do is find the domain of h of x, which is f plus g of x. So again, by definition, this property, the domain is going to be the intersection of the domain of f and the domain of g. So if I want to take a look at the domain of f and g separately, the domain of f, sorry, let me write this down correctly, domain of f is going to be all real numbers. We know that because it's a polynomial with no domain restrictions. The domain of g, however, will not be all real numbers. We haven't done this in a little while, but we did take a look at the domain of root functions. Remember that inside the root, the value has to be greater than or equal to 0. So it cannot be, that value cannot be negative. That would give us imaginary numbers. And in these functions, imaginary numbers don't exist as part of the domain because the domain is graphic. So what we may notice here is that the domain of g is actually x must be greater than or equal to positive 2 if you add 2 to both sides. So if we were to take this to a number line, the domain of f, the domain of f would shade everything to the left and to the right, including 2. It would shade everything. The domain of g would have a closed circle at 2 and shade everything to the right. So we can see where these two overlap is everything to the right of positive 2 and including 2. So the intersection of the individual domains makes up the domain of h of x. So the domain of h of x is going to be x is greater than or equal to 2. It is where these two functions, or these two domains of the individual functions overlap. Part B says to find a new function rule for h of x. So let's go ahead and evaluate h of x using the definition. So h of x is, again, f plus g of x, which is the same as f of x plus g of x. And you wouldn't necessarily have to write down all of the steps, but that allows us to take x squared and add to root x minus 2. Now, unlike the last problem, This one cannot be simplified. So this is going to be our function rule for h of x. If I wanted to write h of x as a function, this is what it would look like. Now let me go ahead and take that to the graph, because this is not any type of a function that we've probably really looked at this year. And if you take a look at the graph here, you can see that the function has a value starting from the right and going up. I could zoom this out a little bit. And you can see that it's going to the right forever. So it started at +2. It had a number here at +2 on the x-axis, and it goes right forever. So our domain was accurate here. Now in evaluating h of x, part C, we have different options. But since we already have a new rule for h of x, I'm going to go ahead and use that rule. I'm just going to go ahead and substitute in 3 for x. And so I can show this substitution here and then let the calculator do that hard work for me, the little simplification. And we can see that the domain, or h of 3, is equal to 10. Now again, you could have done this differently. You could have first found f of 3 and then added that to g of 3. So f of 3 is 9. G of 3 would be the square root of 3 minus 2. And so you'd have 9 plus 1. And you'd end up getting 10. So you can evaluate the functions individually, or you can evaluate them together. Either or would be, you can evaluate them individually and then add them together, or you can use the function rule for h of x to evaluate. Either or will get you to the same answer. So if we take a look at D, I'm going to go ahead and evaluate using the function rule. So I'm going to substitute in a -1 into the function rule that we wrote in part B, and then simplify. So in this case, I'm going to get -1 squared plus the square root of -1 minus 3, which would be -4. Square root of -1 would be +1. Remember, the square root of negative number is imaginary. And so the square root of 4 would be 2. So h of -1 would be 1 plus 2i. Now the reason we are showing imaginary units in this case is that I'm not worried about the graph here, just the evaluation. So I can simplify this into an imaginary unit. Now, if we were to take a look at this graphically, if we were to plot h of x as a function, what we would find out is that h of -1 on a graph could also be considered undefined. Now, the reason it would be undefined is because we have an imaginary unit there. So if we were worried about just the input value to the output value would be an imaginary unit. But if we were focused on more the graph, and you can see it here on the calculator, you have an undefined value there at -1, or a value that does not exist. So depending on how the problem is approached, you could have a couple different answers for the evaluation there. Now let's go ahead and take a look at products and quotients of functions. Products and quotients of functions work very similar. The only difference here is that with quotients of functions, we have to be careful that we do not have a 0 in the denominator. So we can still work through the domains of the functions the same way. We can still work through the creation of a new rule and the evaluation of units in the same way. But the domain is where we have to be careful of if it's a division problem. If it's a division problem, we have to make sure that there is not a 0 in the denominator. So we're going to see an example like that. Let's go ahead and take a look at example 3. It says determine, for A, determine the domain of h of x if h of x is f times g of x. Now we have f and g of x listed above. So first we want the domain of f. Well, again, remember that 1 plus x has to be greater than or equal to 0 since it's inside a square root. So the domain of x is actually going to be greater than or equal to -1. The domain of g in this case, what is inside that square root also has to be greater than or equal to 1. So 3 minus x must also be greater than or equal to 1. In this case, you'd have -x is greater than or equal to -3. Dividing by a -3, x has to be less than 3. So our domain for our new function, the domain for h of x is going to be where these two functions overlap. And these two functions overlap from -1, including -1, to 3, and including 3. So the domain of h of x is going to be from -1 to 3, including both of those values. Is we are combining the two functions. So h of x, h of x again is f times g of x. And what that means is we can multiply the two different functions for f and g. So this would be the square root of 1 plus x times the square root of 3 minus x. Now remember, with root functions, if they are both the same types of roots, we can multiply together their radicands. So essentially what we would have is 1 plus x times 3 minus x within the root. So if you do the distribution here, you'd have 3, a negative x, a positive 3x, and a negative x squared. So within the root, h of x would become the square root of negative x squared plus 2x plus 3. And this would be the new function rule. Now, if you wanted to, we could go ahead and check this on the graph. So we could graph the square root of, again, negative x squared plus 2x. I'm sorry, let me get that in there correctly. Square root of negative x squared plus 2x plus 3. Taking a look at the graph, you can see here the domain does match up with what we did in part A. So the domain of this would exist between -1 and +3. So then in part C, it says to use the result from part B to evaluate h of 2 and h of 4. So again, this would be the substitution into the function of h of x. Now let's just go ahead and let's do that entirely on the calculator. So that would be the square root of negative 2 in parentheses squared plus 2 times 2 plus 3. And we can see the result here would be a decimal. So what we need to do is we need to evaluate this by hand. So we can simplify essentially what's inside the square root. So we can take negative 2, square that, plus 2 times 2 plus 3. And that value would be 3. So h of 2 would just be root 3 in its exact form, which we can see the decimal approximation here. H of 4 would follow the same pattern. And so we can repeat this process, but substitute in for 4 for x. And we would get the root of -5, which would be 5i, or root 5i. Now, as we saw this previously, if we were dealing with a graph, we could have h of 4 as undefined. So if we approach this as inputs and outputs of the function, we could use the imaginary unit. But if we were talking about or focusing on the function on a graph, that value would be undefined. Finally, the last question, problem 4 here, is a division of the two functions, or of two functions. So h of x in this case is going to be f divided by g of x. Again, when finding the domain, we want to first identify the domain of f and the domain of g. The domain of f is going to be a quadratic function. And without any domain restrictions, it's going to have a domain of all real numbers. G is also going to have a domain of all real numbers, as it is a linear function. Now, the domain of h of x in this case is the overlapping of those two values, which would be all numbers. However, we do have to take consideration that x minus 3 is actually going into the denominator. So x would actually be all real numbers except for 3. Because if 3 was one of the zeros, or one of the values of the domain there, we would have a 0 in the denominator. So as we saw in that rule here, in that property, we do have to consider any value that would make the g of x, or the denominator, 0 and restrict that from the domain. We saw that with rational functions, so that just continues that idea. Now in problem B, it says to find a new function rule for h of x. So this goes again back to what we saw a little bit with rational functions. H of x is the division of f and g of x. So what we can do is we can put them into a fraction. X squared minus x minus 6 over x minus 3. If we want to simplify this, the numerator would become x minus 3 times x plus 2, and the denominator would become x minus 3. Now we can simplify this function if we want to. So we can write h of x as x plus 2. But what we have to realize here is that x cannot equal the value 3. Now again, this x cannot equal the value 3 because x minus 3 was at one point part of the denominator, and we cannot have a 0 in that denominator. So if I graph the function, let me go ahead and graph the original function that we wrote here. So let me graph x squared minus x minus 6 divided by x minus 3. What you're going to see is that it's going to look like a line. However, when I go to the table and take a look at x equals positive 3, we see an error there because that would be a hole as part of our line. So there would be no value at x equals 3. Finally, the last thing that we have to do here is evaluate h of 3 and h of 0. So when evaluating h of 3, we can already list this as undefined because x cannot be 3. So that's an important thing to note, that even if we simplify the expression, as we did simplify the expression, that we do take note that x cannot be 3 because of that factor that was at one time in the denominator. So h of 3 would be undefined. H of 0, in this case, we could put in 0 for x, and we'd have 0 plus 2. So h of 0 would be 2. You can also check those in the graphing calculator by looking at the table of the graph and comparing x and y values. So what we can see here is that the domain in all cases when we complete arithmetic with the functions, it's going to be the overlapping of the domain of the original pieces, except for if we have a denominator. Then we have to make sure that we account for that domain restriction. This is a good place to stop. When we reconvene in class, we'll have an opportunity to take a look at some more example problems and then answer your questions. As always, thank you guys for tuning in, and we'll see you soon.